We flip a switch and the lights just come on. It feels so simple, right? But behind that switch, there is this incredible hidden world, a massive, brilliantly engineered system of wires and towers that's constantly working to keep our lives powered and, most importantly, safe. I mean, have you ever really stopped to think about it? How does the power from a plant, maybe hundreds of miles away, travel all that distance just to light up your lamp? It's a heck of a journey across this vast network built with layer upon layer of engineering, all designed to protect you. Okay, so that journey, it all starts on what we call the electrical grid. And you really shouldn't think of it like a local road. No, this is more like a nationwide superhighway, but for electricity. So here's the deal. To move electricity efficiently over hundreds of miles, you have to minimize how much power you lose along the way. And the solution is to send it at an incredibly high voltage, or what engineers call extra high tension. I mean, these towers are carrying power at over 132,000 volts. That's fantastic for long distance travel, but it's way, way too dangerous to bring into your neighborhood. So, how do we tame all that wild, high voltage power and make it safe enough for our homes? Well, the answer lies in a really crucial device called a transformer. And you know what? The concept is actually surprisingly simple. A transformer is basically the off-ramp on that electrical superhighway we were just talking about. It takes all that fast-moving, high-voltage power and steps it down, slowing it to a much, much safer level before it can be routed into your neighborhood. Now, the power doesn't just drop from 132,000 volts straight to your wall outlet. No way. It's a gradual, staged process. First, it steps down to around 11,000 volts for those local substations you see around. Then, a final transformer brings it to a much lower, safer voltage for our homes. You see? Each step just makes the power more and more manageable. Okay, so now that we get the big picture of the grid, let's zoom way in and look at the physical pathways themselves. The cables that carry all this power are so much more complex than just a simple piece of copper wire. They are really their own self-contained, multi-layered systems. Seriously, every single medium and high voltage cable is a marvel of material science. Each layer is meticulously designed, meticulously manufactured, all to do a specific job. And they're all working together to achieve two main goals: maximum efficiency and absolute safety. All right, let's break it down. Right at the very center, you've got the conductor. That's the actual metal path for the electricity. Then that's wrapped in insulation to keep all that power contained. Next is a metallic screen, which is a key safety feature connected right to the earth. And then the whole thing is wrapped in a tough outer sheath for physical protection from, well, everything. The choice of that insulation layer is a critical engineering decision. Older cables often use PVC, but the problem is it can become brittle over time. Modern cables, on the other hand, use a material called XLP, or cross-linked polyethylene. It's just a superior insulator. It can withstand higher temperatures, which means the cable can safely carry more current, and it has a much longer lifespan. Okay, so we've talked about all this incredible engineering, but what is the single most important safety feature in this entire system? It's not some complex device or a fancy new material. It's the one that connects the whole system directly to the planet itself. It really comes down to a simple principle of physics. Electricity always seeks the easiest path to the ground. So if a fault happens, like a wire comes loose, grounding provides that path. It's a safe, low-resistance escape route. All that dangerous current gets directed harmlessly right into the earth, preventing shocks and fires. Now, there are a few ways to create this connection. The diagram here on the left, that shows chemical earthing, where a copper rod is driven into the ground and surrounded by special conductive minerals just to improve that connection. Over on the right is plate earthing, which involves burying a large metal plate deep underground, often with layers of charcoal and salt to maintain conductivity. They look different, but the goal is exactly the same: create a super low resistance path for any fault currents to escape safely into the earth. So the journey of electricity is almost over. It's traveled hundreds of miles, it's been transformed down to safer voltages, and now it's flowing through protected cables right inside your walls. But there is one last crucial device standing guard over every single circuit in your home. You probably know this device. It's that little switch in your breaker box that trips when you plug in too many things at once. The miniature circuit breaker, or MCB, is an incredibly important, life-saving piece of technology that acts as the final gatekeeper for electricity entering your home's circuits. But here's the thing, not all circuit breakers are the same. They're chosen specifically for the job they need to do. A B-curve breaker, for instance, is very sensitive, perfect for simple things like lights. A C-curve is built to handle the medium power surge from a device like a refrigerator kicking on. And for something really heavy duty, like a water pump with a huge startup surge, you need a tough D-curve breaker. It's all about matching the protection perfectly to the device. So, from a giant tower miles away, through transformers, inside armored cables, protected by a connection to the earth, and watched over by a tiny breaker, it's all one massive hidden system. An incredible feat of engineering designed to do one thing: safely power our world. It's definitely something to appreciate the next time you just flip a switch.